Well logging is a fascinating technique. It involves lowering specialized instruments into a borehole. These instruments are often called tools or sondes. They meticulously measure various properties of the rocks. These measurements also assess the fluids within these rocks. This process provides a continuous record or log. The log plots these properties against depth. It is like creating a detailed diary of the Earth's subsurface layers. This diary helps us understand what lies hidden beneath our feet, often miles down. The importance of well logging cannot be overstated. Imagine trying to find a specific mineral deposit, or perhaps pinpointing an underground water source. Without well logging, exploration would be like searching in the dark. It provides essential data that guides crucial decisions. This reduces the risks associated with drilling. It also significantly cuts down on exploration costs. For example, oil and gas companies rely heavily on logs. They use them to decide if a well is worth completing for production. Historically, early methods of understanding subsurface geology were quite basic. Geologists would primarily examine rock cuttings. These cuttings were brought to the surface during drilling. While useful, this method offered limited insight. Modern well logging, however, is incredibly sophisticated. It employs advanced physics and cutting-edge technology. This technological evolution has revolutionized our ability to see underground. We can now gather precise data on rock composition, porosity, and fluid content. This was unimaginable a century ago. The primary purpose of well logging extends beyond just resource hunting. It is fundamentally about acquiring detailed geological information. This includes identifying different rock types like sandstone, shale, or limestone. It helps determine the porosity of these rocks. Porosity is the space within rocks that can hold fluids. Crucially, logging helps identify the types of fluids present. Is it valuable oil, natural gas, or simply salt water? This comprehensive understanding is vital. It supports not only resource extraction but also environmental studies and civil engineering projects. The instruments used in well logging are marvels of engineering. These tools, or sondes, are typically long cylindrical devices. They are packed with sensitive sensors. These sondes are carefully lowered into the borehole. They hang from a strong armored cable known as a wireline. This wireline serves a dual purpose. It supports the weight of the tool. It also transmits power down to the tool, and it sends the measurement data back up to the surface in real time. Each type of sonde is designed to measure specific rock or fluid characteristics. Electrical logging tools are among the most fundamental. Resistivity logs, for instance, measure how well rocks conduct electricity, or, more accurately, how much they resist electrical current. Hydrocarbons like oil and gas are highly resistive. Saline water, or brine, is conductive. This difference helps distinguish between oil-bearing zones and water-bearing zones. Another electrical log, the spontaneous potential (SP) log, helps identify permeable rock layers. These are zones where fluids can flow more easily. Such zones are often good candidates for reservoirs. Nuclear logging tools provide another set of crucial measurements. Gamma ray (GR) logs measure the natural radioactivity present in rocks. Shales, which are fine-grained sedimentary rocks, often contain radioactive elements. Sandstones and carbonates usually have low radioactivity. Thus, GR logs are excellent for differentiating shales from potential reservoir rocks. Density logs and neutron logs are also nuclear tools. They help determine rock porosity. This is the percentage of pore space in the rock. They can also help identify gas in these pores. Acoustic logging tools, often called sonic logs, use sound waves. These tools emit pulses of sound. They then measure the time it takes for the sound to travel through the rock formation. This travel time is related to the rock's density and elasticity. From sonic logs, petrophysicists can calculate porosity. They can also identify fractures within the rock. Furthermore, sonic data is used to assess the mechanical properties of rocks. This is important for understanding how strong the formations are. For example, it helps in designing safe drilling operations. The data collected by logging tools is presented as a series of curves. These curves are plotted against depth. This graphical display is known as a well log. Interpreting these logs is a specialized skill. It is typically performed by geologists and petrophysicists. They analyze the patterns and values of the different curves. This analysis turns raw measurements into meaningful geological information. It is like reading a complex language. Each curve and deflection tells a part of the subsurface story. It requires careful study to understand fully. One of the primary pieces of information obtained is lithology identification. This means determining the types of rocks present. Different rock types respond differently to logging tools. For example, shales typically show high gamma-ray readings. They also show characteristic responses on resistivity and porosity logs. Sandstones and limestones, common reservoir rocks, have lower gamma-ray values. The combination of density, neutron, and sonic logs helps to distinguish between these various rock types. This forms the basic framework for understanding the geology. Porosity is another critical parameter derived from well logs. Porosity refers to the void spaces within a rock. These spaces can hold fluids like oil, gas, or water. A good reservoir rock must have sufficient porosity. Several logging tools help estimate porosity. Neutron logs are sensitive to the amount of hydrogen in the formation. Since water and hydrocarbons contain hydrogen, this helps measure fluid-filled porosity. Density logs measure the bulk density of the rock. Knowing the rock matrix density and fluid density allows porosity calculation. Sonic logs also contribute to porosity estimation. Finally, well logs help determine fluid saturation. This tells us what proportion of the pore space is occupied by different fluids. For example, what percentage is oil and what percentage is water? Resistivity logs are paramount for this. As mentioned, oil and gas are resistive, while salt water is conductive. By analyzing resistivity values, alongside porosity information, experts can estimate hydrocarbon saturation. For instance, a porous sandstone with high resistivity might indicate an oil or gas reservoir. This is a key step in evaluating a well's potential. Well logging plays an indispensable role throughout the life cycle of an oil or gas field. During the exploration phase, logs are critical. They help geoscientists decide whether a drilled well has found hydrocarbons. They identify potentially productive zones, often called pay zones. This information guides decisions about further testing or drilling. For example, if logs show good porosity and high hydrocarbon saturation, the well might be tested. This significantly reduces the financial risk of drilling dry holes. It makes the search for new resources more targeted. Once a discovery is made, well logs are essential for reservoir characterization. They provide detailed data to define the extent and quality of the reservoir. Logs from multiple wells can be correlated. This helps create a three-dimensional model of the underground reservoir. This model shows its thickness, porosity distribution, and fluid content. Such understanding is crucial for estimating the total volume of oil or gas in place. It informs the planning of how the field will be developed. For instance, where to drill additional production wells. The utility of well logging does not end once production begins. Specialized logging techniques, known as production logging, are used in producing wells. These logs help monitor what is happening downhole. They can track the movement of fluids within the reservoir. They can identify which zones are contributing oil or gas. They can also detect problems, such as unwanted water production. For example, if a well starts producing too much water, production logs can pinpoint where the water is entering the well bore. This allows for remedial actions. In conclusion, well logging is a cornerstone of subsurface exploration and resource management. It provides a unique window into the Earth's hidden layers, from identifying rock types and porosity to quantifying valuable hydrocarbons. Its applications span from initial discovery to optimizing long-term production. It helps companies make informed, cost-effective decisions. It also contributes significantly to our broader geological understanding. Without the insights provided by well logging, our ability to find and utilize essential resources like oil, gas, and groundwater would be severely hampered. It truly unlocks the secrets held deep within the Earth.